In this part 1, we use first-order differential equations on the total population in country that we choose, which is Maldives from 2003 to 2023. To find the growth of population in Maldives, we apply the MAT097 model. This model assumes that the rate at which total population increases at a given time is proportional to the number of population at that time. The MAT097 model can be written as dP over dt equal to Kp, where P is the number of population, T is the time in years, and K is the constant. The objective of this task 1 is to find total population in Maldives from 2003 to 2023 at any given year, and also to predict the future and past value of population. Lastly, it is also to identify the reason why the expected population is not exact as recorded data that we took from the official website.
This is our table of data of population in Maldives from the year 2003 to 2023 that we retrieved from internet. We can see that as the year increases, the population in Maldives also increases. This shows that the population in Maldives is growing. Next, this is our table of data of population in Maldives using particular solution. We substitute the t with 0 until 20 to get the population in Maldives. The data obtained also shows that as the year increases, the population in Maldives also increases. This is the two graphs that we obtained from our actual data and particular solution, which is PT equals to 296,491 times e to the power of 0.02996t. The green graph represents our actual data, while the blue graph is our data by substituting t equals to 0 until t equals to 20 in our particular solution. We can see that both graphs are almost the same and close to each other. This means that our data has a low percentage error.
Next, moving on to discussion, this is how we calculated our particular solution. First, we let PT equals to the number of population in Maldives at time, where we use t as the variable and it is in the unit of year. Since the rate of population is proportional to the number of population, we use the equation dP over dt equals to Kp, where K in the equation represents the constant proportionality. Second, we integrated both sides of the equation, which becomes integration 1 over P dP equals to integration K dt. After integration, it will become ln modulus P equals to Kt plus C. And then we will change it into exponential form, which becomes e to the power of ln modulus P equals to e to the power of Kt plus C. After simplifying it, we will get P equals to plus minus e to the power of C times e to the power of Kt. Third, our general solution becomes the simplified version of the equation that we got in step 2 just now, which is P equals to A times e to the power of Kt, where e to the power of C is equals to A. Using the initial condition where t equals to 0, which was in 2003, our P becomes 296,491. Then, our general solution becomes P equals to 296,491. We also calculated and found the value of our constant K by using t equals to 10, which was in 2013, and our P is equals to 4070. We substituted t equals to 10 into the equation in step 3 just now, and we got K equals to 0.02996. Hence, our particular solution now becomes PT equals to 296,491 times e to the power of 0.02996t.
Prediction future and past. We already have the particular solution, which is P bracket T equal to 296,491 exponent power of 0.02996 time with T. For the future, we take T as 30, then substitute back into the particular solution. We will get 728,375. For the past, we take T as negative 10, then substitute back into the particular solution. We will get 297,738.
There are several questions for task 1.
First, are the values calculated from the particular solution accurate with the actual value? No, because the constant k was only rounded off for decimal places, which caused a small error in the calculation. This leads to a difference between the predicted value from the Malthusian model and the actual value, resulting in percentage error. Second, find the percentage of error. Calculated value minus with the actual value over actual value times with 100. 8,540,202 minus with 8,521,030 over 8,521,030 times 100, getting 0.22 percentage of error. 3. If there is any difference between the actual value and the value calculated from the particular solution, why do you think it is so? Yes, because the formula only calculates population growth and doesn't account for unpredictable events like disaster or economic changes. It also doesn't consider factors like emigration or immigration. 4. What has affected the population growth in the past? First point, high birth rate. The Maldives has achieved substantial reduction in maternal and child mortality rate, with nearly all mothers giving birth in established health facility assisted by skilled provider. 5. What do you think might affect the population in future? First point, climate change and rising level. The Maldives is made of a very low-lying island. If sea keep rising, some island could become uninhabitable, that forcing people to move or even leave the country. Overall, we fully achieved the goal of Task 1. We clearly understood how to apply first-order differential equation learned in the MAT097 course to our project. Using this method, we calculated the population growth in the Maldives from 2003 to 2023. We compared the estimated value based on the Malthusian model with the actual population data and calculated the percentage error. This helped us understand why the estimate didn't always match the real number. We also looked into the real factors that affect population growth. One of the main benefits of Task 1 was learning how to use maths tools like the Malthusian model to solve real-world problems.
For task 2, numerical method, we need to solve the equation given using Simpson's rule. Simpson's rule is where we search for the area under the curve by splitting the region into uniform rectangles. This is the complete tabulation data for 7 ordinates that can be made by using Excel. The first step is to find the value of h, which the formula are h equal to b minus a divided by n, and in Excel you can calculate it by entering the command as shown in the video. Next, we enter the value of x. The first value is 0.2. As for the next value, we can determine it by adding it with the value of h. Make sure to put a dollar sign as shown in the video to get the value. Then, we need to find the value of fx. We need to insert the value of x into our equation to find fx value for each subinterval. The command power are used to make x power of something. Then, we need to enter the coefficient for each subintervals, which always start with 1 and end with 1, while 4 and 2 will alternate between them. Next, we search for coefficient fx by multiplying the value of fx and its coefficient. Lastly, sum all the value of coefficient fx and calculate the area under the curve by using the Simpson's rule formula.
This is the graph illustrated by the function with 7 subintervals using Desmos. As you can see, the vibrant color is the area under the graph between the limit.
Next, for 9 ordinates, we repeat the same step as before, but we change the number of intervals, which is the n values equals to 8, and we use the same formula, h equals to b minus with a divided by n equals to 0.225. For x table, we put the first value, which is the a value, is equals to 0.2, and the next x value, we increase it by h values, and don't forget to put dollar symbol to keep the h values fixed. For fx table, we just insert the function equation, which is ln 9x to the power of x minus x power of 5. For coefficient tables, for the first and last ordinates, we put the coefficient of 1. For even ordinates, we just put coefficient of 4. And lastly, for the odd ordinates, we put coefficient of 2. Next, coefficient multiplied with fx table, we just need to multiply fx values with coefficient values, and we get the coefficient multiplied with fx values, and we sum it and got 47.781169. Lastly, to get the area under the curve, we use the formula h divided by 3, and multiply it with the sum that we calculated before and got 3.583588.
This is the graph illustrated by the function with x sub-interval using Desmos. As you can see, the vibrant color is the area under the graph between the limit.